Hello, everyone. Great to have you. Hope you enjoyed your lunch. I certainly did. Desserts were quite good, actually, I must say. So my name is Bruce Momjian. I'm one of the Postgres core team members. I've been working with Postgres for 20 years now. Seems like a long time. Work for Enterprise DB, one of the sort of companies supporting Postgres. Simon made that point this morning about companies supporting the community. So it's exciting to be here. This is, I guess, as Steven said, my 6th time as well, because I've been to all of them. And this is certainly, I think, one of the best we've had of a PG Open. I love the venue. I think it's just a really great setup, the way we have everything working here. And obviously, the organizers are doing a really great job. So today, we're here to talk about Postgres indexing, specifically flexible indexing, specifically non-traditional indexing. And I think it's a very interesting topic. We have a good number of slides and a lot of sort of brain twister kind of concepts I'm going to throw at you the next 50 minutes. But you know, I have to start out with a disappointment. I'm actually giving a talk tomorrow afternoon called Non-Relational Postgres, and you might have heard Simon mention it this morning. In a lot of ways, this presentation goes with that presentation. So I'm going to be alluding to a couple things as I go through this presentation that may not be clear to you, and it might be clear if you were also able to attend tomorrow's talk about non-relational Postgres. It's the last talk of the day tomorrow, and it goes very, very well with this. In fact, ideally, I should have had them move that talk today, and then I could have done the indexing afterward, but I realized that this morning, so a little too late to be switching talk orders around. But this concept really of flexible indexing, I think, is one of the powers of Postgres. It's similar to the non-relational ideas of Postgres. The idea, and Simon did a great job this morning talking about it, of taking on non-traditional workloads, of taking on problems that typically aren't solved in the relational space, the relational database space, but Postgres solves. Things like GIS, things like full-text search, things like very complicated analysis of arrays and all that other stuff. It's really cool that Postgres does that. And actually, a lot of this indexing has come from Oleg and his team in Russia, so it's good to have him. He's sitting right there. It's good to have him in the audience as well to back me up. So let's talk about what we're going to cover today. First, we're going to talk about traditional indexing. This is sort of the bread and butter kind of stuff that all relational systems do to one extent or another. And then we're going to branch out a little bit. We're going to talk about expression indexes. If you might have heard those before, you might not be sure what they are. They're actually really powerful, and I'm going to show you some examples of that. Then we're going to talk about partial indexes, which also sounds kind of bizarre, but has some really cool use cases. We're going to talk about what a bitmap scan is, which is sort of a hybrid of a traditional index scan. I'll explain why that's important. And then we're going to kind of go out into space, go away from even traditional storage of indexes and talk about some of the non-Btree index types that Postgres supports. We'll talk about the data types that need that support, and then we'll finally talk about the use of indexes and kind of how to analyze them and then wrap it all up. And again, if you're able to attend my talk tomorrow, we get a lot more concrete about the specific data types that Postgres supports, the specific workloads where a lot of these indexes become useful. I will take questions during my speech. So again, if you want to have a question, just raise your hand. I'll repeat the question and be able to answer it for you pretty easily. So let's talk about traditional indexing. This is what pretty much all the relational systems do. And the bread and butter index, of course, for relational systems is Btree, short for binary tree. It sort of has, everyone's used to the standard chart that has, little tree at the top, the root, and then it kind of goes all down. The Btree has been around for a long time. It has a lot of use cases. It's a very generic. It doesn't handle every case, as I'll show you later, but it handles a lot of them. But it's really ideal for looking up unique values and also maintaining uniqueness in an index. So if you're looking for a specific order number or a specific customer number or a specific part number, if we think of the traditional OLTP cases, Btree is just great. It takes a huge problem space, a huge number of rows, breaks it down, gets you to that particular row you're looking for as fast as possible. Now, there's a lot of use cases that don't have that kind of requirement, but if that's your requirement, Btree is great for it. Our implementation is actually a hybrid of Btree called NBtree. It has very high concurrency. It handles some of the traditional problems that very much older Btree implementations have in terms of keeping the tree balanced and so forth. Those are all handled very well. It effectively stores a key and a pointer to a row in the index. So if you think of what's actually in that index, it's basically just the key, the value, the part number, the order number, the customer number that you might happen to be indexing, and then where is it? Where is it in the heap? Where is the row that matches that value? And it also can support things like order by. If you ask for, like, for example, the 5 highest customer numbers or the 5 earliest employee numbers, we can actually use the index for that. We can use it for merge joins, and we can use it for the inner side of a nested loop, which again is getting beyond what I normally cover, but effectively the optimizer can use these indexes as well to get you queries. So even if you aren't specifically identifying a column that you want to, you're not saying order ID equals 12, right, which you hope is going to use an index. If you have an index on order ID, you're hoping that's going to be used if it's reasonable. But in fact, even internally, if you don't even mention the order ID column equals a constant, you do a join on the order ID column, the optimizer can make use of that Btree index as well. Okay? But you might say, okay, that's cool. That's what everyone else, that's what all the other databases do. What more do you have? Quite a bit. We can index things like expressions and functions. I'll show you some example of that. We sometimes need better control of the rows. Sometimes we need a small, lightweight index. And Btrees are pretty heavy. If you imagine you're storing every key and then a pointer every heap, Btree is kind of heavy. I may need a lighter one. You might want closest match searches, not an exact match, but I want the things that's closest to that. You may have an index with many duplicates, and Btree is not really great if you have a lot of duplicates. Think of a column that has true or false, okay? Btree is really not going to help you there, right? Male or female, whatever. It's just not going to help you because you don't have really that kind of unique, I'm looking for one row, you're looking for, half the table is true or false. Obviously, the Btree is not going to help you there. And some of the multi-valued fields also don't index very well with Btree. And through this talk, I'm going to talk about some of the examples of actually how our non-traditional indexes make that possible. Any questions? Okay, great. Okay, so first thing that's, I would say, is non-traditional. It's a little hard to get your head wrapped around, but they're called expression indexes, okay? I've been around databases for, I guess, 30 years now, and, they're traditional, well, maybe not 30, maybe 25. But the traditional way that you index something is you index a column, or you index a couple columns, right? It's a single column or multi-column index. It's pretty straightforward, okay? However, a lot of times you're doing things in your query that don't match a single column. And here's an example where I'm looking for the name Andy that could be uppercase, could be lowercase, I don't know. So I'm basically going to say I want any case in this for a top query where the lowercase of name equals Andy lowercase. Now, if I create an index, as you can see here in the second query on the name column, and that actually doesn't work. Because effectively what's happening is if I do the top query, it's saying, well, you didn't really ask for name equals Andy, you asked for lower of name equals Andy, and your index doesn't have that. Your index just has the name unadulterated. So the solution, as you can see in the last query, is to create an expression index. Now I'm using a function call here. I could have used arithmetic. I could have used concatenation. I could have used random, I don't know, whatever, okay? I could have used almost anything. I can use like toChar and then a type, some kind of timestamp column, and I want to index just the year or whatever. I could have done a whole bunch of cool things. I could have indexed the day of the week of the particular thing. And again, as long as I use that particular same function in my query, it'll work. So that's an example, a very simple example. I'll show you some more complex ones in a little minute. So here's an example of a customer field. There's an example of an actual run. We create a customer table. We put 1,000 customers in there. So pretty straightforward. And then we ask for customer, Then we ask for customer 999. Okay, and that works. It matches the first index. The first index being customer name, okay? And it works fine. But we try the second one on this table, and we notice that lower customer doesn't work. It does the sequential scan, it doesn't use the index. That's because it's a brand new table. We only have that one index on it. Now, if I create an index on the lower of the name, then when I do this query right here, you can notice I'm getting an index scan at the bottom. Okay? So I'm not saying you're going to use these expression indexes day one, but when you start to write queries that have comparisons that are more complicated than a single column name, expression indexes can get you out of a lot of jams. In fact, a lot of people, what they'll do is they'll take a whole bunch of columns and kind of mush them together. Like maybe I'm only an index like the first 3 letters of the field, and then I want some other part of some other field, concatenate, all these crazy things that people do. It actually allows you to kind of make things indexable that traditionally were not indexable. Okay? So you can use user-defined functions in these expression indexes. You can concatenate. You can use math expressions. The function has to be immutable. That's a requirement because you are indexing a particular value that can't change every time you call the function, or effectively the index would be useless. And also there can be casting issues you might need to look at. Okay? Any questions? Okay. Yep. Okay, so second one, partial indexes. This is a little different than expression indexes. This is a case where you only want to index part of a table. Because remember, when I normally say create index, it indexes every row, okay? But that may not be what you need to do, okay? What if I'm only going to be looking up a subset of my data? Why should I index every single row if I'm only going to look up a couple of them? For example, when I used to do accounting, we used to have like an accounts receivable table, like a whole bunch of transactions. And there was a Boolean flag that said 0 balance, true or false, okay? And honestly, every time you ran an accounting report, you only wanted to see the non-zero balance entries. The ones that 0 balanced are old. You didn't want to see them. So I could have created, I didn't have Postgres at the time, but I could have created an index that just indexed the ones that didn't have 0 balances, because those are the ones I want to show in my report. Didn't make sense. 99% of the entries had 0 balances. Nobody wants to see those, right? Accounts receivable report wants to show what's receivable, not what's zeroed. So it will allow you to kind of slice up your data and index only the parts you want to. That means that you have less, the index is smaller, more of it's going to fit into RAM, and also you don't have the overhead of maintaining an index for rows you're never going to be looking up. So again, smaller, more shallow, less update and insert overhead. And you can still do a sequential scan if you don't use the index, so the data's still there, it just isn't as indexed. So here's an example. We're going to add a state column to the customer table, okay? Unfortunately, I'm in Dallas, so Arizona's not that far. Well, in Dallas, it's Texas, it's really far. But I mean, in the map, it doesn't appear as far as it does from Philadelphia, right? So we're gonna make customers who begin with 9 be in Arizona. So we had 1,000 customers. 10% of our customers, we've assigned them to Arizona. And what I can do is if I really care a lot about my Arizona customers, I don't know why, maybe there's a tax reason, maybe I have to run a special report just on Arizona customers, whatever. I can create a special index. Now, this is not an expression index. This is a partial index. And you can see here I've used a where clause. I say create index on customer, state column, where state equals Arizona. So I've only indexed my Arizona customers. I can still query the other customers, but I can't use this index to find them. Okay? And if I run a query and I say, give me all the customers who live in Pennsylvania, because I happen to live in Pennsylvania, I get a sequential scan. So the data's still there. I just can't use the index. But if I ask for Arizona, boom, I get the index. Okay? Again, not something you're going to use on day one. But as you go forward, you start to be like, oh, yeah, this would really, really cool. Why am I indexing everything? This would be a great way of doing a whole bunch of cool stuff. Okay? Now, that example was a little contrived because I'll back up. I ended up creating an index on the state column, and my where clause also had the state column. See what I'm saying? Like, my restriction is the state column, and I'm indexing the state. But there's no reason I have to do it that way. So I could, this is a lot more useful, I can index the name column, and I can restrict it to Arizona. So now I kind of have the best of both worlds, right? I can go right to the index and know that every person in that index is from Arizona by default because of the where clause. Then I can index something else. So if I look at the query at the bottom, that one doesn't do anything because I haven't restricted it to Arizona, right? There's no way. It's like, well, I could give you some of the people who are customer 957, but I can't give you all of them because I don't know which ones are in Arizona. But if I do a query like the top one, I ask, give me everyone in Arizona and that customer number, it all of a sudden uses the index. And what's interesting, if you look at the index condition, it's checking the name. It doesn't even mention the state because it already knows they're all in Arizona, right? So in a way, I've used the index twice. I've used the index because by default, I know they're all in Arizona. And now all you really need to do is to go and look at the name. Okay? Kind of crafty, I think. And if you look at the bottom, you can still look up everybody in Arizona just fine. Just go look in Arizona and boom, it'll still look them up. Even though I didn't ask for the name there. I didn't mention the name at all, but it was good. Okay? Any questions? Yes, sir. Does a partial index use a bitmap scan? I am going to answer that question in a minute. So thank you. Next question. Okay, great. Okay, bitmap scan. Hey, wow, you lined me right up here. So what is a bitmap scan? Again, we're looking at some of the non-traditional aspects of Postgres indexing. Because normally when you use an index, what we do is for every index match, we go directly to the heap. So every index match, we get the match, we go to the heap, we make the match, go to the heap, get the match, go to the heap. If there's a lot of index matches, you're going to that heap a lot of times. So in normal OLTP, that's not a problem. You only have one customer, so you're only going to go to the index once. You have one order number, you're only going to index once. But there's a lot of cases where that doesn't work, particularly when you're getting a lot of index hits, a lot of index matches. So when you're getting, and you see this a lot with OLAP, with data warehouse type queries, which are saying, give me all the blue shirts, and all of a sudden you get, tons of shirts, right? When you're starting to get a whole bunch of hits, that idea that you go right from the Btree to the heap is kind of inefficient. So we came up with this idea of a bitmap index scan. It's not a bitmap index, just to clarify. Bitmap index is a very rigid index that has little bits for each one, and it's hard to add, and it's hard to update and keep consistent. That's not this. This is an in-memory bitmap that we create when we expect a lot of matches. And this gentleman pointed out that most of the examples from this match, from these partial indexes, actually had a lot of matches. We know there's 100 people in Arizona, right? In fact, it tells me, or actually it tells me, it thinks there's 5, but anyway, it knows there's more than 1, so it starts to use a bitmap. So again, it's a way of reducing a lot of the overhead when we have a lot of matches. It also allows us to use multiple indexes for the same query. I'll show you an example of that. So it basically creates a bitmap in memory, either at the row or block level granularity, and then it allows us to visit the heap once rather than multiple times in case we have multiple hits on the same page. Okay? We can merge bitmaps together, and it's automatically enabled. You don't have to do anything to do this. So here's an example of a multi-column index of using multiple bitmaps. What we do is we have a restriction on index 1. It creates a bitmap. We happen to also have a restriction on an index on column 2, separate index. And we can create 2 bitmaps and merge them together. And using that, we can actually take multiple indexes, use them in the same query, on the same table, which, again, very common for data warehouse. But again, you don't have to be using a data warehouse query. It could be any query. The optimizer will automatically select these if it finds it's useful. Okay? Any questions? Good, great, good. Now we're going to, again, head to space. That's why I used the term before. We're going to go for non-Btree index types. And again, it looks kind of like this picture. It's kind of, whoa, kind of craziness. Let's look at the first one. This one is fairly new. It was introduced, I believe, in 9.5. And it is BRIN indexes, or block range indexes. I mentioned earlier when I talked about it that there's a whole bunch of cases where you'd want like a lightweight index, one that doesn't take a lot of RAM, one that isn't very heavy, expensive to update. This is your baby right here. Okay? Very popular for data warehouse applications where you may have indexed every column in the table. I'm not saying you can't put a Btree on every column in a table, but you probably should think twice before you do that. Okay? Btree indexes can be very large, and if you index every column in the table, your Btree indexes can be much larger than the table itself. And aside from storage, you have a lot of overhead. Every time you do an insert, every time you do an update, you've got to maintain those Btree indexes. Okay? BRIN eliminates that a lot and gives us a way of creating this lightweight index on columns that probably don't need a Btree, but I'd still like to have an index on them. That's kind of the logic behind it. So the indexes are very small. It basically stores a minimum maximum value for a range of blocks, typically 1 meg. So you've only got 2 values for every meg of data. That's pretty small, okay? It basically allows you to read through a big table and skip very large sections of your data. It's ideal for naturally ordered data, but it's not a requirement. The index is 0.003% of the heap size, typically. Okay, and that's percent, so it's not 1%, it's not 0.1%, it's 0.003%. And you can get a sort of an understanding, because in many cases, I'm going to show you an example later, sometimes the Btree can be bigger than the heap for a very narrow table. Btree can be bigger. This is 0.003% the size. We're going a completely different direction. Indexes are inexpensive to update. You can actually index every column at very low cost, and lookups, it is a little slower. So you have to accept that. I'm going to show you an example in a minute, but right now I'm just going to go through the index types, and we'll show you some examples. The next one is GIN. This stands for Generalized Inverted Index. I know the letters don't quite work, but pretend the N is like one of the letters after the I, basically. It's best for indexing values with many keys or values. For example, text documents, a lot of words, a lot of lexemes, we call them, tokens in a document. So you want to index all of them. That's a case where we have a lot of values in a document. JSON, you're going to index keys and values there. Again, a lot of values for a particular document. a particular column. Multidimensional arrays, multidimensional data arrays, again, many values in a single column. GIN is very ideal for that type of storage. Very good for cases with a lot of duplicates. Optimized for multi-row matches, and I'll show you some examples in a minute. Key is stored only once. So if you have the word Fred in your document, we're only going to store Fred once in the index. I don't care if it's in 10,000 rows. There's only going to be one word Fred in the index. I'm going to show you how that works in a minute. But again, when you have a lot of duplicates or you've got a lot of documents with a lot of duplicate values inside a column, this really shines. Indexes are stored with the key and then running values of the rows. I'll show you an example. Index updates are batched because usually this is a very expensive update operation. We have a very slick way of doing that thanks to the Russians. And we've had some major improvements in 9.4 for this, particularly compression, thanks to Alexander Kurtov. Compression of row pointer lists and optimized multi-key filtering, again, are in 9.4. If you're running that or later, you'll find that they're much faster than previous releases. Final one, well, actually the final, but one of them, generalized search tree. This is, as it sounds, generalized. So it's not like GIN, which is primarily looking for duplicate cases, or, and it's not like Btree, where you're going to binary search everything. GIN is sort of for everything else that doesn't fit. That's how I think of it. It's very good for things like geometric types, range types, age store, trigrams. These are cases where Btree doesn't work, GIN doesn't work. The gist allows you to basically create your own. And thanks to the Russians, they've thought of a bunch of cool ways to index these things. And we're obviously the beneficiaries of that over the work they've done in the past 15 or 17 years. And we wouldn't be the same without these features, that's for sure. Supports things like distance operator, nearest neighbor. So you can do things like give me all the 5 closest pizza shops to a particular location. That's usually very hard to do in SQL. It actually works very well in Postgres and is highly optimized, which I think is exciting. Again, and I'm going to talk about this more on tomorrow, but effectively the concept you start getting is that Postgres is taking the relational sort of standard and then sort of reaching for the stars, right? Reaching way beyond sort of the staid sort of capabilities that everyone assumes a relational system can do, and now starting to do things that no one else does. And you have people adopting Postgres now because it does things that no one else does. And I think that's going to get more and more common as we go forward. SPGIST, this is a different version of GIST. It's space partitioned, which sounds really cool. It effectively allows you to sort of work around some of the limitations of GIST for particular types of data. There are some data layouts that are particularly hard to represent efficiently in GIST. And space partitioning kind of allows us to sort of reduce the search space and kind of it stores the data sort of in a different format. I'm not going to go into huge detail here, but again, it is another option. Hash indexes, I'm leaving this for last for a reason I'm going to get at in a minute. They're very traditionally used in relational systems. Postgres hash indexes are not that good. Our Btree is so good that the hash indexes are really not that much of a benefit anymore, so we don't encourage their use. They are not crash safe, so effectively if server crashes, you'll actually potentially get an index corruption when you bring the server back up. So as of 9.6 or 9.5, when you try and create a hash index, we will issue a warning when you create the hash index to say, are you sure you want to do this? Basically, because it's embarrassing. We do have some people working on it. We haven't ripped it out, although maybe we should have years ago. Somebody is working on making them crash safe. They're not replicated. They can't be restored with point-in-time recovery. Their performance is not good. Their concurrency characteristics are not good. Just a big boo, right? Just Boo. Yes, sir. Why not rip it out? So the reason we haven't ripped it out is because every time we go to rip it out, somebody who's really smart, and it's usually a different person each time, shows up and says, I will fix it. And they, yeah. And they technically do, okay? They technically make them better in some dimension of better. So they'll fix the concurrency problem. They'll fix the, they'll make them faster to build. They'll make them faster to look up, right? Still, they're not crushing Btree, but they're still like a little bit, if you look the right way, you can see it being faster. And that's why we haven't gotten rid of it. We do have somebody who's seriously looking at making it crash safe. And I think if we can get through that thing, but there's no way we would have accepted this had it come in brand new. There's no way. It took me years to get the warning. So when you try and create it, you get a warning. So that, it is what it is. I'm trying the best I can. Let me ask over here. Yes, sir.
If they were implemented well, like you had a hash index type and it was implemented in a way that you would have accepted today, would that be of real value?
So the question is, if we had a hash index that was really implemented well, would it be of value? And the answer is we don't know, because the Btree code has been so optimized, right, that we don't really know what, if we had a hash that everyone was working on, if we could get it to pass better than Btree, okay? So it's kind of like it's this we don't know problem that it's possible somebody can sprinkle some fairy dust on it and it would be faster. But until we actually see it, we don't know, and it's hard, it's difficult to justify ripping something out when theoretically it should be faster, if that makes any sense, yeah. But there's also concurrency problems, which are a little harder to work around, because the way Btree's set up, it spreads the data out so far that you don't have as many concurrency problems. There's a lot of research of how to do that in a concurrent way. Hash has some of that, but the structure itself makes it harder to do some of those cool things. Multiple rows within the same hash bucket would cause contention. We have I think we've made hash improvements probably every 2 years for the past 10 years or 12 years. Yeah.
What I can't understand is why we don't convert that to Btree, or just syntax shit around the hash.
So why don't we internally convert to Btree? I think hope springs eternal, basically. There's a sense that, and honestly, the people who come to resurrect hash, these guys are these are really smart people. And I just can't go up against them and say, well, you're wrong, because I'm probably wrong, right? And maybe there's going to be some magic pixie dust out there somewhere. But we keep waiting, and every time somebody improves it, they do improve it. If you look at the release notes, I think in 9.6 we increased the number of default hash buckets. So all of a sudden, we get a lot less contention, and we had a super huge, super small number of hash buckets, and I think now it automatically doubles the size of the hash buckets it does a whole bunch of crazy stuff that's actually getting faster. So I don't know. It's sort of a philosophical issue at this point, I would say. Question over here, I'm sorry. Okay. Right, so the question is, should we just take it out? Well, my point is that it took me years of suggesting to get the warning. So it's hard to imagine I'm going to get an approval to rip it out. I just don't. It's not going to happen, particularly because we have sites that are using it for particular use cases, and all of a sudden, if we just took it out, then the indexes would just not work anymore, and then we'd have to put it away. And obviously, people do care about it because they keep improving it. So I guess as long as I'm making little baby steps and the warning's there, hopefully, it doesn't really catch most people. It's usually the novices. People come in brand new from other databases. They're like, oh, I want a hash index on that. I'm never going to be doing greater than. They assume from other systems that Postgres is just the same and then reuse it. And at least they're going to get a warning now. But I'll also say we don't get many complaints about it either, which is odd. Like we don't get very complaints of, oh, I crashed on my index, hash index is corrupt, or I don't even get complaints that it's not replicated. I just doesn't seem to, I just don't hear them. So I guess if I had a lot of complaints, we would do something, but in terms of general complaints about it, I don't hear it, and I guess it's, I don't know. I don't know why.
Every time Henry Hurton talks about indexing, they've got a slide like this. We're like,
Yeah, just the boo slide, yeah. So this is, this is dirty laundry.
so maybe you're not hearing it because no one's using it anymore.
Well, then that means at least we're communicating. That's good. Yes, sir. What is use? I don't know. There is no use case. There's no use. People, let me put it this way. People smarter than me say just stay around, so it's staying around.
If you're indexing an image, let's say, like a megabyte, the only case where it can outperform Btree is when the thing that you're indexing is very, very long.
So if the key is very long, then the hash would be smaller, yeah. That's a good point. Yes, sir.
I would think that it would also have somewhat similar performance characteristics to Btree's in many cases, and yet have a lot smaller on disk size.
Right, so the question is, it would be similar to if it was done properly, it would be similar to Btree, but have smaller disk size. That's also true. The build time is often smaller, should be potentially smaller, although I think right now it might not be true. So again, I have no formal computer science training. I've read a lot of books. So some of the guys who are really, the guys, they don't want to take it out, so it's not going anywhere. Yeah.
And the thing is, it predates having expression indexes, so now you can just create a Btree of an index of the CRC hash.
I see.
Yeah, that's what I'm arguing, that the hash function, like the functionality should actually just do that for you.
Right, so the argument is that it should, for large values, it should auto-hash it. And in fact, I'm going to go to the next slide. I can't talk anymore about hashes, but I'll say that we actually have an index, a GIN index, which hashes the JSON. So exactly what you're saying, it auto-hashes. Okay, let's move forward. I'm not making this up. If you do that query right there, those are your index types, okay? Built into Postgres. Okay? So let's take a look. Btree is great for unique lookups. Brin is ideal for indexing many columns, small, lightweight. Okay? GIN's ideal with many duplicates. SPGIST ideal for indexes whose keys have many duplicate prefixes. Okay? And GIST for everything else. That's how I kind of think of it. I'm not even mentioning hash. Okay, so let's take a look at data types. Data type support, again, be covering this more in detail tomorrow. Here are all the data types that support Btree. That's a lot of them, okay? You see integer, varchar, text. No, text isn't there. It's actually bpchar over there. Let's see here. Timestamp, date time, float, integer, interval, a lot of them. Pretty much everything. No, not everything, but a lot, almost everything. If we look at Brin, little smaller, but still very impressive. Notice the word MinMax, because again, it stores the MinMax for a range of blocks, so many of the ops have those names. GIN, pretty small, right? What is that, 4? That's what we got, okay? But it really kicks on those. So don't sneeze at it. If you have that data type, this is what you're going to want to use. Extensions I don't think I have listed here because I didn't install everything when I ran it. It's a good point. And GIST, these are the other ones. And what you can see here are the geometric types. I have not installed PostGIS, but PostGIS would also use these. And some of the text search ones can use it, although we probably recommend GIN in these cases. Okay? SPGIST, a little smaller, again, related to just some specific data types. So, index type examples. Btree, this is the standard layout, okay, of the way Btree is normally stored. You've got a root one, internal one, local leaf ones, and then they point to the heap. Here's an example of Brin. I'm creating a table here with 100,000 rows, and 100 million rows, I'm sorry, and I'm going to create a Btree index, and I'm going to create a Brin index. And when I look at the bottom, the table itself is 3.4 gigabytes. The Btree index is 2.1 gigabytes. Ouch. Okay, again, it's only a single column, so there's no data there, but it's still really hulking big. The Brin index is 104 kilobytes. That's accurate. That's kilobytes there. So the one's in multiple gigabytes. The other one is 104 kilobytes. And that's obviously dramatic. Gin, again, I said Gin is very good for duplicates, so I'm going to use a text search example here. What I basically got is I created TS vector column. I put the fox is sick, and how sick is this? If I look at the actual table, it has basically taken the string, converted them to lexemes, and then stored those in the table. Okay? And if I look at the index, the Gin index, effectively what I have is the word fox, this, how, and the are once, and the word is and sick are twice. Remember I said if you had the word Fred, it would only show up once, no matter how many rows had the word Fred? Well, sick is here twice, okay? Sick is here twice in 2 rows, but I only store sick once in the Gin index because it's the key and then all the matches, okay? And obviously very well for optimizing things like full text search and so forth, okay? Integer arrays also are indexed the same way. You would index, multiple values from there. Here's a JSON example using Gin. The other big use for Gin indexes. So I've got a Bill true, Bill active, and Jack also active. If I look at the JSON at the bottom there, there's Bill and Jack. But when I actually create an index on it, in this case a JSON B index with ops index, which is the default, what I have is I have Bill and Jack at the bottom appearing once, and I've got active, name, and true appearing multiple times. I only store those once, and I store all of the matches. So again, same concept I went to before, where you're doing Gin and you're only doing one key and multiple matches for that. Okay. There also is a different type of index you can create for JSON on Gin. It's called JSON path ops. What it effectively does is to hash the entire path, the JSON path. So in this case, I am hashing name Bill, name Jack, which are unique, and the key, the sort of path active true actually appears twice. Okay, I only record it once. There are some advantages with using one or the other, but effectively, you can read the docs. It has to do with whether you think you look up a whole path, or whether you need to look up individual keys that may exist at different places within a document. Okay. Gist is, again, loosely coupled values, also things like geometric types, range types, IP network types. Here's a linear example. A linear example is very easy to do for Btree, because like if you think like a Btree, it just orders everything, right? Just, from smallest to biggest, it's easy to figure out where everything goes. Try and do that in a graph, right? This is trying to give you some of the challenge of what you need to do here. So like I could do, what if I have all these points? How do I do that? How do I get it into Btree? Because what would I do? X is greater than 2, but there's no representation of the Y part, right? So I'm only indexing one component. That's why Btree just doesn't work. Effectively with gist and geometric types, you create things called bounding boxes. So you have a big box that goes to smaller boxes, which goes to smaller boxes, similar to the way Btree works, right, where it gets big and big ranges and smaller ranges, but instead of the ranges being linear, they're now boxes. Did you get that? So when you do Btree, it's always a linear on one axis. Effectively, they're doing kind of the same thing as Btree, but it's boxes that are getting smaller and more detailed as you go down. Okay. Again, amazing work done by Russians. Originally, the code came from Berkeley, but it's been drastically redesigned over the years. And again, it's sort of an R-tree representation. You can now imagine if I'm looking for a certain point, I go for the big box that has the point, then I go for the smaller box that has the point, Then I go for the smaller box that has a point, and then I can find my points. Okay. Very good for two-dimensional stuff, obviously box, circle, and obviously GIS uses this as well. For ranges, also very good with GIST. If you've ever dealt with range types, I'm not going to cover that, although I will cover it tomorrow. So stay tuned if you're going to be around. But it allows you to sort of do the same kind of complexity as we did with R-tree boxes, with bounding boxes, but now the bounding boxes are ranges. Okay, so think of it, the bounding box is kind of, instead of being X, Y, it's now start and stop, and we now have boxes of ranges where certain ranges fit in certain boxes. Very, very interesting. Again, hard for me to kind of conceptualize a lot, but if I think about it enough, I can figure it out. SPGIST, a little different. This is a case where we're actually indexing prefixes. So in this example, I've got URLs, which start with HTTP in a lot of cases, starts with FTP in a couple other cases. Actually, these are URIs, technically, because there's FTP there. And what I can now do is I can kind of segment my strings now based on the prefixes that are common among a whole group of rows. Okay, very good for long values that we want to kind of chop up. It's not used that much. I think a lot of people don't understand it sometimes. But I'm trying to correct that here. But there are some definitely cool use cases for it. Again, these are cases where traditional Btree storage or the normal GIST wouldn't work well. You can imagine that. QuadPointOps is used. It's just, again, a different type of bounding box. Uses 4 corner points in a square of decreasing sizes, so it's just a little different. It tries to avoid some of the problems for particular data. Certain data layouts have trouble with GIST, so the QuadPointOps helps with that. KD points splits on only one dimension. I'm not going to go into that. We do have extension support for these index types, which I talked about earlier. We already mentioned PT trigram, actually supported by GIST and GIN. PostGIS, of course, HStore, InArray, LTree Cube, and so forth. These all support the native, super cool index types that we have. Any questions? Wow, yes, sir. So why are some of the index types and extensions and not? So it's actually these index types are in Postgres. It's merely support for the data types that's in the extension. You see, so GIN and GIST are in Postgres, but we have to write, if we add a custom data type, we have to teach GIN and GIST how to store those data types. And that's why they look like that. And the reason they're extensions is because not everyone wants PostGIS in their database, not everyone wants Cube in their database or HStore. I think that's a good reason. Yes, sir?
That being said, Btree, GIN, and Btree GIST are something that could be in core, right?
Yes, so Btree, GIN, Btree, GIST, could they be in core? In fact, they could. We do have somebody in Russia who's working on, it's a woman who works for Postgres Pro, and she's working on sort of optimizing some of the Btree code to handle cases with a lot of duplicates. And if we did that, then we probably wouldn't need Btree GIN, which, as you imagine, is really designed to handle duplicates really well. In a traditional Btree format, we can get rid of it.
Does that allow, the reason I was asking, the time that I've had to add Btree GIN, I think was the case where I wanted to do is use string, and you're indexing both an integer and then an array.
Okay.
So it needs the Btree ops to be able to.
Okay, so the gentleman's basically saying he had to use Btree GIN once when he had to mix GIN with another column that also had GIN, and it kind of pulled them together, I think. So yeah, there are some crazy cases where you still would need it. That's a good point. So let's finish up with index usage summary. Again, this is a lot less technical than kind of the earlier part. When do you create indexes? When you have a lot of sequential scans, maybe. Take a look at the pgstat user tables for that. You can use explain to see which indexes are being used. Sequential scans are not only always bad, but again, you have to use a little wisdom when you get in there. PGStat user indexes, if the value is low, for index scan, the index might not be used. If the value is 0, it's never being used. So keep an eye on that. You know, index use, creating indexes is great. Removing unused indexes, it's also great. So don't think always adding is good. Removing is also good. And then unnecessary indexes use storage and slow you down. When you're evaluating index type, you have a couple things to consider: the time to build it, and the overhead of maintaining it, the size of the index, the access speed, and then the flexibility. How useful is that index? And that is my last slide. This is actually a pachinko parlor in Japan. I have run out of time, so unless there's any final questions, I'll be glad to be up in here and answer them. I appreciate you asking questions while I spoke, and I hope you have a great conference. So thank you.